Okay, the main premise of this lab is that the difference between Diet Coke and regular Coke differ only in one ingredient, and that's sugar. And we're going to test that hypothesis or that premise in this lab. But first, we want to see how the third liquid we're testing, okay, compares to the three. So I'm going to have my youngest student take the cans, let's go, and put them in the aquarium. And we're going to see clearly that once he's out of the way there, the Diet Coke floats and the regular Coke sinks to the bottom. This is the instruction and introduction to experiment or lab 2 density of liquids. So for those that don't have the objectives, I know one of my class does, I'm just going to review them pretty quickly. And you would say number 1, 2, determine the density of water, Diet Coke, and Red Coke. Number 2, determine the grams of sugar or carbohydrates in a can of Coke, which by the way will be 355 milliliters. So we're going to determine the densities of regular and Diet Coke and somehow through that data calculate the grams of sugar in a regular can of Coke, which is 355 milliliters. Number 3, determine the accuracy of your results using a percent error. Okay, let's review the objectives. We're going to find the density of water, Diet Coke, and regular Coke. How are we going to do that? Well, if you look at your data table, okay, very simply, we're going to eventually get to a data table. And we're going to start with water. Water, you're going to get it from the tap, and be very careful turning the water on in the sinks in the back. They're under a spigot that will produce high pressure for aspirators for AP Chem. So taking the water out of them, just go very slow, okay? And that'd be one way we get the water. That's the way we're going to get the water. So now, we can't pour the water directly on a triple beam balance, obviously. So what you're going to do is you're going to take a container. That container is going to be a beaker. So take a 250 beaker, which is at your table, okay? And you'll take a beaker, which is a basically a holding device for liquids, and you're going to mass that beaker right on a scale. That's your container. Okay, and you're going to get, of course, grams. Then you're going to mass the container and the liquid. Well, to get the liquid, you're going to have to measure 100 milliliters. So you're going to take your graduated cylinder, okay, however it looks, and you're going to measure to the 100 mark. Now, I marked out 100.0 because we need to keep 4 sig figs. If you were to put 100, we'd have 1 sig fig, and when we do our densities, all 3 liquids would come out to be 1 gram. So it's very important that you measure out to 100.0 to that level of precision. That's why I reminded you. Please use something called pipettes. They're little plastic bulbs at the end that will top off your level to get as accurate measurement as possible to that, or I should say precise as possible, to that 100.0 line. If you have extra, take some out. All of these materials can be dumped in and out of the sink, no problems. So once you measure 100 milliliters of the liquid, 100.0 milliliters of the water in this case, you're going to be doing the same thing. You're going to put that volume into this beaker, and now you're going to measure the beaker and the volume again right here. Obviously, it's going to be heavier. To get the mass of the liquid, you probably guessed you're going to subtract these two numbers. This is the heavier value, right? And this is the lighter value. So the difference between these two, okay, would give you that value. Volume of the liquid we just have, density, of course, mass over volume. This is an easy one. Look at the units, grams per milliliter. So you have the mass of the liquid that you're going to get here. That, of course, is your mass. The volume, of course, would go here. And look at our value. Make sure that your densities have the appropriate level of significance in terms of sig figs. Okay, so both of these. Now this is a gram per milliliter. Let's go over this conversion. This is an important conversion. Now we're going from grams to liter. Okay, let me talk about this for a second. Let's pretend I'm a princess and we get 1.010 grams per milliliter. Okay, that's 4 sig figs. Now, how can I convert that into grams per liter? Well, I know some people say, wow, it's going to get smaller because we're going to a bigger number with liter, but that would be only if it was liter. This is grams per liter. Watch how I do this. This is very important. It's something I've watched over the years students get wrong. Let me put my number I have, 1.010 grams over a milliliter. We're going to do a converting factor. What do I want to convert to? Well, I want to convert to grams over liter. So my friends in chemistry, this has to be a milliliter up top, right? Now, why am I doing that? Because I want to get rid of milliliters and I want to get liters. Okay, so what's my converting factor from milliliters to liters? Well, 1 to 1,000, right? Smaller unit, bigger number. So notice how I set that up. Milliliters cancel, and I'm left with that times 1,000. Okay, and of course that answer is going to be 1010 grams per liter. Notice the number got bigger. Look at this. This was a unit was grams per milliliter. That's how much mass per milliliter. It's only 1, and that makes sense. The density of water should come out to be 1. We've talked about that. But if now I have a liter of water, should I have 1,000 times more grams? Since you're saying in this case that water is about a gram per every milliliter. Divide by means per. So this should be 1,000 times more. People who move the decimal place will get this wrong, okay, by thinking. By using your units, you can figure this out. Intuitively, this makes sense. If I only had 1 cubic centimeter of water, it's about 1 gram. Well, if I have a liter, we learned 2 days ago that a liter is 1,000 cubic centimeters, so it should get bigger by 1,000. A lot more water should be a lot more grams, and that's how you do the conversions. Careful, I have 4 sig figs here. To have 4 sig figs here, and these are just numbers I made up, I would have to put a point there. Okay, so that conversion is very important. This is where I'm looking for correct sig figs. Okay, and you do that for regular Coke, and you do that for Diet Coke. And that's the important pieces of data for objective number 1.
So in the back of the room we have this gray tray, and this is going to be our reagent table. We have 3 liquids we're trying to get the density for, so it would really be prudent if we stagger which liquids we start with. So 1 table or 2 tables can start with Diet Coke, another table can start with regular Coke, another can use water. And when we're using water, make sure, if you're using the tap water, make sure you turn this on slowly, because too fast it's going to come out like a jet and spill all over. So turn it on gently to fill up your container. Now, of course, we're going to measure using a graduated cylinder. Graduated cylinders are more precise than beakers. Beakers are just holding containers. Now, when we measure, of course, we're eye level, but more importantly, party people, we're trying to get 100.0. Okay? Now, we may not pour exactly, so we're going to use in this green tray here these plastic pipettes, barrel pipettes they call them, and you're going to top off by adding more liquid or taking liquid away in order to get the exact 100.0 for significant figures that we need. And you can pour the extra down the drain. The water, of course, and the Diet and regular Coke all can go down the drain in this lab. Okay, no problems. Now, once we have measured our liquid, we have to mass our liquid. Now, of course, we can't pour the liquid on the triple beam balance. That'd be silly, but I've had someone do that, believe it or not. You're going to take a dry beaker. Now, this beaker, okay, you can mass out. And I'm not going to mass it out here, but you can mass it out once and use that mass 3 times if you'd like, and that's part of your design if you want to talk about that. And of course, once you have the mass of the beaker, pour in the liquid, okay, and of course find the new amount of grams from the triple beam balance, and what you're going to get there, the difference of those 2 masses is the mass of your liquid. Mass divided by the volume, which is 100.0 in this lab, gives us our density, and we're going to do that for the 3 liquids. Okay, no problems there. All right, make sure that we wash out and try to dry these the best that we can. So wash out your beakers, especially with the sugar, Coke. Diet Coke and water is easily cleaned out, but this is the one you use the sugar in the Coke tends to really make a big mess. So make sure you wash out your containers, because if you use dirty containers, okay, in this process, then you're going to contaminate your results. If you're doing the density of Coke, okay, with a lot of sugar that it has, a lot of carbohydrates, and then you do water, but you don't clean this out, isn't the water going to be a little more dense than it should be? Yes, you have to be very, very careful to make sure you don't contaminate your results, making sure that when you do this test wash out your graduated cylinder and your beaker. And that's all there is to it. Okay, make sure when you're done everything is clean for the lab group in front of you, and you can go on to the next part, which is the calculating of how many grams of sugar is in a can of Coke. Thanks.